So this talk is titled DuckTyping, Metaclasses, and Recursion, Building a DeepCollection Type. What a mouthful, right? So this is going to touch on some things a lot of developers find kind of intimidating or scary to various degrees, but they're all in the language for a reason. They can be used to great effect sometimes. I'll also say at the outset too that part of the mission of the library that I made for all of this is to generalize something. And if you're working for a company or doing a job, you probably most often don't want to generalize your code. You want to be narrowly scoped to what you're trying to do, because generalizing is hard. If you take your 5-point ticket and get it done in a month because you generalized it, your boss probably isn't going to be very happy. So there's a time and a place for it. You might encounter it sometimes at your work, but it's encountered very often in library writing. All the libraries that you're used to and familiar with pip. So the thing that we're trying to generalize now is handling large or cumbersome data. Things that are deeply nested, and maybe we know what they are, maybe we don't. We encounter stuff like this all the time in APIs and infrastructure as code, in data science. Sometimes applications have internal structures, and it's not just dicts and lists. Sometimes there's tuples in there, or double-ended queues, decks, whatever you have. But handling stuff like this is really common. So we're going to quickly go over a little bit of prior art. So there is this library that was made several years ago called Dict. Dict did a couple cool things. You can pass it your dictionary, create a new object, and then you can, I'll just keep copying. You can start calling aspects, you can start drilling down into the data in your object by dot chaining. That is pretty cool. It's just a little bit of syntactic sugar though for this, right? It's, if I can type. That's basically the same thing. There's not a ton going on there that's really novel, a little bit. It's fun enough. Maybe if that's your preference, you get a kick out of Dict. But there's some issues with what Dict can handle. So if we look at our structure we had up here, we had company, employees, contact info. So there's some fields with dots in them, and we're using dots as a separator in this path. So when we try to do the same thing, it fails because company.company doesn't exist. We need company.company name. So Dict has a solution for this. They've got a separator object, a separator field here in the function that you can pass. Oh, wait, no, they don't. Originally, we made this .dict from a function they gave us, but we need a different API to use a separator. I think that's a bit of a limitation. It's not a very friendly API to expose to people, but it does work. So we can give it a different separator, and now we get our company name out of this nested dict. Cool. Let's try something a little bit different. Let's start with something that is a list off the bat. It still contains dicts and lists. I'm going to quickly copy that over and make a .dict version of that. And we can't. .dict needs a dict. So there's a few limitations in this prior art. Then came along Python Benedict. I first encountered Python Benedict very recently, actually. They announced themselves on Reddit in the Python subreddit, so I took a look at them. And they were doing some of the things that I wanted to see have done. So we try to make a Benedict dictionary out of this thing too, but it fails right off the bat for a similar reason. There's this company .name thing. But Benedict is at least eagerly erroring on it, saying we don't know how to handle that. So we pass it a separator again. Okay, great. And now we can still access something in it in this path-like way, but they're using a / separator now instead of a dot. Okay, good enough. Let's do a little test though. Let's find something else interesting about these. We can try to find out the type of the .dict thing that we got, and it's not actually a dictionary, it's its own thing. So if you're trying to work with dictionaries, and you want to be able to use is_instance to know that you have a dict somewhere in your code, .dict actually doesn't pass that test. You don't have a dict. So that could be a little annoying. Benedict succeeds here. A Benedict is a dict. Great. That could be useful. And Benedict has another power. You can search into your nested dict to find something. And part of the deal here is we have a big cumbersome data structure and we either don't understand it, we don't want to have to stare at it forever, maybe we kind of do understand it but we don't want to type the whole thing out, we want a little shorthand. So Benedict helps us out. Oh, but again, there are some issues with Benedict. Again, you can't pass a list to something and have it become a dict. It's not in the name. So there's some issues. What do we really want? We want something that can handle any type. We want to be able to take a nested structure. We don't care what type it is, and we want to be able to have certain handy features attached to that structure that enable us to introspect and traverse that structure. But we also want to preserve typing. If I start with a dict, I want it to act like a dict. If I start with a tuple, I want it to act like a tuple. Is_instance should work. And I want to, so I kind of want a subclass, basically, is what it sounds like. I want something where I can subclass dict, have it be this deep thing and act like a dict, but I also want to be able to subclass list and tuple and retain all the typing that comes with all of that. And I want better traversal. I don't really like having to deal with this separator thing. This bit right here is kind of handy. Depending on how you like to type things, you may prefer to traverse a structure like this, but it's not too different. But if I pass it in iterable, that looks more natural to me as a Python developer. And it's easier and more natural to construct. So maybe I can actually programmatically create these paths and dig down into it. Now, if I really want a goal, what I want is pattern matching in the structure to traverse it programmatically. Again, I don't need to know what the structure is. I just want a thing that's inside it. Think about the talk 2 talks ago. We had all this health data. It looked nasty, right? I don't need to understand what all is contained in all of that. I just want to be able to dig in and get what I want. That'll have a little bit of an issue if I have pattern matching like that, because what if the field contains asterisks or something like that, so I still need a little bit of support, but it's got a better default. Okay, so now we're going to get into how we do all of this. There's a few things we can try. So this is a class factory made from a function. Show of hands, whoever has indented class before in real code that lived? A few. I'm actually kind of surprised by how many raise their hands, but still most people know, right? It's not a thing you commonly need to do, and it's got some real benefit. With it, we can create an object out of this list, get something new. We've got this DeepCollection object we're creating, and it is in fact a list instance. And we can pass it a dictionary as well, and we'll get back a dictionary instance. So we've got dynamic inheritance here. Again, You don't normally want to do this, but sometimes you really want to leverage some of the strengths that Python has naturally. Python is a very dynamic language. I love type hinting. Static typing, when you can get it in Python, is fantastic, but some things are naturally dynamic, and if you leverage that, you can get a lot out of it. So there's a problem here with this class factory. This class isn't really exposed to you. You can't get it back without creating an instance, which means you can't subclass it, and you can't directly access the class to add on your own methods and pass that along the chain. So how do we get a class without a factory function made from a? How do you get a factory function class without the function? The answer is you use a metaclass. Again, I think metaclasses are pretty uncommonly used. A quick refresher, a metaclass is the class of a class. So if we have just standard old class here, it's instantiated just by typing that class foo pass. The class exists in the namespace. If we instantiate the class, we say, these parentheses here create an object out of the class. So you have a class, you instantiate it to get the object. But Python is hiding from you a little bit the fact that even just writing this, you're instantiating the class. So if you have a metaclass, you can create how that's done. So if I type class, we'll just go foo again, class foo, class bar, metaclass equals foo, pass, and then get rid of that thing right there. Create a little init dunder. And for these purposes, we don't care what happens here. All right, we get init. I didn't instantiate anything the normal way. All I did was tell Python that bar uses foo as a metaclass and the init function was called. So, okay, that's kind of how metaclasses work. You saw, again, a couple talks ago, the call dunder method. That is this right here. In a normal class, if we go up just a bit again to this, we can instantiate a class like so. And then if I put parentheses on that again, that would call the call dunder method. So on the metaclass, this is the same thing that's called when you instantiate a class in the first place. If you can wrap your heads around that. It's a little bit of recursion just baked into what's going on with metaclasses inherently. So if this is invoking call directly, that means I can use it to pass in a new object, and the metaclass can dynamically create my class with the object I gave it as a type. So that's what's going on here. I'm collecting args and quargs and call, and I'm extracting the thing I'm passing in as the base object I'm building from. It could be a dict or a list. I'm getting the type of that thing, dict or list. Then I'm using the type function to create a new class. You use type sometimes to type check things, but the 3-argument form creates a new type. So we create the new type, we call new on it, and then init in order, and then return the instance of that new type. It's kind of complicated, but this will work here. And then finally, when I'm in the type that uses the metaclass, I'm going to call init and pass the original object. So the idea is if I start with a list, I preserve that original list item and use it to populate through the old type. Let's try it out real quick. Okay, now let's see here. Okay, so this looks like a list so far. It is in fact a list. Great, that is what we wanted. And I can do the same thing with a dict. Okay, cool. So now all the methods, thank you. So now all of the methods that list and dict normally have should just come along for free. We don't need to build any of it. And it doesn't matter what kind of object someone's going to create a deep collection with, we're going to mimic it. We're going to bring everything along for free. This is a big step in generalization. We're not done quite yet, because there's a little problem with tuples. What's wrong with tuples? Tuples are an immutable data type. So passing in the object in the init doesn't work. You need to pass it in up here when we call dunder new. Easy enough, we've got it. So we just amend our new bit right here, so we can pass that in. And then we wrap this supercall in a try except, because we still need the supercall some of the time when we're dealing with a immutable object, just not the immutable ones like tuples. So let's modify this a little bit more. Let's try that tuple again. Great. Okay. It's a tuple. Okay, so now I'm dynamically inheriting, but I'm not really doing much that's interesting with this yet. What I really want for that pathing feature that I was talking about before is I want to have special get methods, get item, set item. I want to attach a paths to key method, a paths to value method, and all the values for a particular key. We'll get to all that in time. I'm not going to go through every little bit. But this is where the even more recursion comes into play, and a lot of DuckTyping. So this is a little snippet. Let's see if I can, yeah, I'm gonna have to scroll a little bit here. So there's a paths to key function here at the bottom that we're going to use, and I'm cutting out a lot of logic here, but you see there's a quick test for if the key is itself path-like, like is the key a list, or if it's simple like a string. And then there's calls to separate functions called paths to path-like key and paths to simple key. And we have one of those abbreviated here. So the DuckTyping comes in a little bit here. We're checking for something thinks it's a dict. Okay, great. And then we iterate through all the keys and items of the dict, and if it's not a dict, it's probably a list, so we'll do that. But if we're checking is instance, we're going to need whoever knows how many if statements. So it's not like really DuckTyping. What's really DuckTyping is to just try it. Just try to access dot items and see if it works. If it does, fantastic. Recurse, go further down the tree, because like what Al Swigert said yesterday is like, recursion is horrible, right? We don't want to use recursion ever, except one real good case, which is tree traversal. And that's what we're doing right here. We've got this structure of whatever geometry, whatever type. We don't know where anything is. We need to do a search through a tree. So recursion is the natural fit here, actually. And we're using yields and yield from, so we can make this all generator-like because we don't know how long it's going to take. We don't know how big the structure is, how deep it is. And we don't necessarily want all the things at once anyway. If we do, we can just put the generator inside a list call. But anyway, we have a try and except here to be really DuckTypy. See if it's dict-like. If it's not, okay. See if it's iterable anyway, like a list or a tuple, and get everything out of this that you can. I'm going to pause for a second and reiterate. Generalizing is hard, right? If you know the structure that you're dealing with and it's well-defined, you don't necessarily need all of this. You don't need a lot of try and excepts around DuckTyping if you know the types that you're working with. Don't do all of that. This is going to take you a lot more time to figure out. But there's good reason that I'm doing it, which is I wanted to provide a library that other people could use. Libraries should be generalized fairly often. And if recursion and metaclasses scare you, it might be comforting to know that they're pretty common in a lot of the libraries you're familiar with. Most day job Python programmers don't write metaclasses. But it's in Pydantic. They're using a great metaclass or two. Django uses metaclasses. SQL Alchemy uses metaclasses. Some of the best Python libraries we know get some of their functionality out of the fact that they're leveraging these deeper, uncommonly used tools. Python has a lot of power most people don't need and shouldn't try to use unless they've got a good reason. But I think this is a pretty good reason. We talked about, in another previous talk, the Zen of Python. One of them is simple is better than complex. Totally agree. But what does that really mean to a normal developer? They're using libraries like Pydantic and Flask to make things simple, but that doesn't mean the code inside Pydantic and Flask is simple. Flask has a pretty complicated stack handling mechanism. Pydantic is really complicated internally. So that's what we're choosing to do often, is we're hiding complexity when it's necessary and leveraging it to get us a lot of powerful tools. So yeah, simple is better than complex, definitely. And that's part of why I'm doing this, is so if you have cumbersome data, you can use it simply. You don't need to know how this library was built, but it makes for a fun talk. So, okay, so generalizing is hard, but it's possible. So I've done some of this. These are excerpts from the library that I wrote. Let's see if it can actually do something. So the real thing, I'm not going to scroll through the few hundred lines of Python that it is, but I will prove that it actually does work. So we had, again, remember that that data object. It was this thing up here. The IPython is condensing it a bit for me, but that's what it is. And I access double star here to go down any number of levels to find company name. And I got out a company name. Great. Okay, let's try a few other things. There are zip codes in there. Let's find all the zip codes. And I don't need to know exactly what the name of the key was. It's got zip in there somewhere, so I'm surrounded by more asterisks, more globbing, and I get out all the zip codes. I think that's pretty cool. There's a handy function in there that'll dedupe these things for you. Oh, I miscopied something. Well, I'll figure that one out later. But there is a deduping function that even works for things that are not hashable. There's all of these things often presented to you as generators, and again, you can just get your values out by calling list on this. And these are then all of the paths to the zip code field in our structure. So that can be really handy. And because they're normal lists, that's pretty easy to iterate over and modify if you want. So if you're trying to translate that path into something else useful elsewhere in the same structure or a similar structure, you can see I've had to do stuff like this several times for clients. And then you can get back the values because those paths work. Now, so that's the end of that little bit of the talk, but I think I've got a couple minutes left, so I'm going to show something a little interesting. One more bit of the library. See if I can just explode this. So, Josh Cannon, I think in a lightning talk, you mentioned getAttr. Everybody uses getAttr. No one uses getAttribute. GetAttribute is its twin brother, its evil twin. So the difference between those two dunder methods is that getAttr is lazy and getAttribute is eager. So when you're subclassing something, you want to use getAttr if you want to check if a method exists and then give a fallback for if it doesn't. GetAttribute seizes the first opportunity though. So one fun part in this code base that I can show off is that getAttribute here intercepts every method call and checks to see if that method exists on the parent class. And if it does, decorate it so that we can check and make sure that that parent class method did or did not mutate the underlying structure, and then sync it with the DeepCollection class that we've got. So like list.append. If you use list.append, you're going to add to the list. Well, you can add to a DeepCollection list too, sure. But we need to keep track of what that change is. So we, again, call this ensure post call sync method, and that is a decorator, not with the at syntax, because decorators are functions. We're just calling it right up here so that if our underlying structure changes, we keep it in sync. Sounds simple enough, but this is a complicated bit of code you can go and noodle over later if you want. It took me a little bit to figure out. So that's basically it. And through fiddling with my laptop, trying to get it on the screen, I forgot the introduction to all of this. So real quickly, I guess, you know some of this already because we just went over it, but I hoped that some of what you would get out of this depends a bit on your experience level. There's some complicated stuff in here, but a new person can get something. Hopefully even the experienced among you saw something interesting. And why you can pay any attention to me and you think I know anything about all of this. I've been a Python developer and consultant for over a decade. I've got quite a bit of experience. I run a company that does Python and DevOps consultation, and I'm an open source contributor. I've contributed to and maintained a few projects. So I'm not scared of diving into that general world and that library world. That's where I like to be. I enjoy building things people can use. That is my talk. Does anybody have any questions about all this wild stuff? Yeah, so this is a real library you can pip install and use, and I'm basically announcing it today. And it's ready to use. It is very well tested, and I aim to have it exhaustively test all the built-in types and collection types so that you have no doubt that it actually works across the board. And it handles some third-party types, like you can make a .dict a DeepCollection even. It is called DeepCollections. It's on PyPI. Search for it there. From there, there'll be a link to the repository if you want to check out how the code actually works. Can you say again the library name? I haven't run across that one. I tried searching for other similar things. There's James Path is an older one that's pretty similar to dict. but it has searching features. dpath is another one that has searching features. You can basically do everything in those that you can over in here, but with some of the extra niceties that people didn't consider before, like all this type stuff. And the processing speed in my library is not the focus, it's developer speed. It's making things easy for you to figure out. But if you want speed, a lot of the features here are exposed as functions too, so you don't even need this class stuff. You can just search for the thing in the dict and be done with it. So I'll look at that one later and try and figure out what differences may exist. Other question?
I may have missed it earlier, but does DeepCollection support regex beyond wildcards?
It does. So the default is glob syntaxing, and we use Python standard library fnmatch for that. And it's got the double wildcard for traversing any number of steps. It matches keys and dicts and indices and lists, but you can substitute out that pattern matching for regex or a different custom matching algorithm that you write. So yes. Any other questions? All right, that's my talk.